Have you ever wondered how a robot can look at an image and know exactly what it is seeing, identifying objects like a car, a person, or even a specific tool? Machine learning object recognition fundamentally operates by training computational models to identify and classify objects within images or video feeds, leveraging large datasets to learn distinct visual patterns. The core mechanism behind this capability involves artificial neural networks, particularly a specialized type known as convolutional neural networks, or CNNs. These networks are structured layers that mimic the human visual cortex, processing information hierarchically. Early layers might detect simple features like edges and corners, while deeper layers combine these to recognize more complex shapes and textures. This process of learning from examples, rather than being explicitly programmed for each object, allows the system to generalize and identify new instances of objects it has seen before. Practically speaking, when a robot encounters a new image, it passes through these trained CNN layers. Each layer extracts and transforms features, ultimately feeding into a classification layer that assigns a probability to each possible object category. For instance, it might output an 85% chance of seeing a wrench and a 10% chance of seeing a hammer. A crucial insider detail is the concept of feature maps. After a convolutional layer processes an image, it generates multiple feature maps, which are essentially filtered versions of the input image, each highlighting a specific learned pattern. These maps then feed into pooling layers that reduce their spatial dimension, making the system more robust to variations in object position or scale. The training of these complex networks relies on a process called backpropagation, where the network adjusts its internal weights based on the difference between its predictions and the actual labels in the training data, continually refining its ability to recognize objects. Understanding these principles of feature extraction, hierarchical processing, and iterative learning through CNNs is vital because it demystifies how robots gain their visual intelligence, enabling us to design more robust and adaptable autonomous systems that can navigate and interact effectively with their environments.
If you love robotics, like, subscribe, and keep building with us.